Imagine standing on the edge of everything you have ever known. The space between stars stretches out farther than any road you could travel in a lifetime. Even the nearest star beyond our sun is more than 4 light years away. A light year means the distance light travels in 1 year while moving at the universe's fastest allowed speed. If our fastest spacecraft of today tried to cross that gulf, it would take tens of thousands of years. A journey longer than human civilization has even existed. It is a reminder that the cosmos is built on scales that laugh at rockets and engines and every machine we have ever made. Why is this so difficult? Why should nature care about speed at all? If we can imagine traveling faster than light, why does the universe forbid it? The answer runs deep into the foundations of reality. A century and some years ago, Albert Einstein discovered that light is not simply fast. Light defines the structure of causality. Causality simply means cause must come before effect everywhere. If something were to travel faster than light, then in certain perspectives, the effect could happen before the cause. You could send a message and receive a reply before you typed the original. Every intuition about what can happen first would collapse. To prevent logical chaos, space-time locks the speed of causality to one specific value. That value is the speed of light in empty space. But this constant is not merely about illumination, it is about information. It is about the limit on how fast any influence can propagate. Light happens to be the thing that reaches that exact limit, because light has no rest mass. The empty space of the universe already holds the rule. You can test it with any experiment. No matter how fast you chase a ray of light, you can never gain on it. Light always rushes away with the same speed, not because it is trying to escape, but because space-time rewrites the rules of time and length around your motion to keep the limit unbroken. Time itself slows for objects in rapid motion. Distances shrink in the direction of travel. Physics bends so the constraint can hold. Human instincts rebel at this idea. We think of speed as something absolute. We think if you press the accelerator harder, you should go faster. Yet relativity teaches that space and time are not a static stage where motion occurs. Instead, they are part of the performance. They transform to protect the ordering of events. When you accelerate toward the speed of light, you gain almost no extra speed. All the effort feeds instead into more energy stored in your motion. You can get arbitrarily close, but never cross the threshold. This is where our hopes seem to crumble. If no object with mass can match light, then galaxies will remain forever beyond our direct reach. We appear trapped in a local neighborhood of the universe, locked behind a cosmic border drawn by the speed of light. However, that is a misunderstanding caused by our everyday notion of distance. In the deepest description of the universe, speed is not simply about covering ground. Because space-time is curved by gravity, distances themselves can change. The geometry of the universe can stretch or compress. Two places that were once far can become close. Two events that seem separated can be bridged by bending the structure they exist within. General relativity reveals that what we call gravity is not an invisible force pulling objects. It is the curvature of space-time itself. Massive objects like planets and stars create indentations in the geometry. Lighter objects follow those curves. You feel weight because you are pushed upward by the ground while space-time tries to lead you downward along its curve. In orbit, astronauts feel weightless, not because gravity has vanished, but because they are falling freely along a curved path with no surface resisting them. The key idea is simple but profound. Nothing can locally move faster than light. Locally means within a very small region where the curvature is gentle enough to be ignored. But globally, over giant scales, space-time can evolve in ways that surpass any speed you can imagine. In the first tiny fraction of a second after the Big Bang, the entire universe expanded so quickly that distant regions raced away faster than light could ever chase. Today, we still observe distant galaxies receding from us faster than light. They are not racing through space. The space between us and them is growing. This turns the rule inside out. Light is bound to the curvature of space-time. but the curvature itself is free to do something different. That loophole forces us to rethink the meaning of travel. Perhaps the problem is not that we are too slow. Perhaps the problem is that we are trying to move through space instead of rearranging it. Picture a surfer riding a wave. The water moves, not the surfer, yet the surfer travels swiftly across the ocean. Now picture a spacecraft riding a wave of geometry. The craft rests calmly in the center, while the space behind expands and the space ahead contracts. From the pilot's view, nothing unusual happens. There is no engine pushing you, no violent acceleration. Inside the ship, you would feel as peaceful as someone sitting still. But from the outside world, your vessel would leap across immense distances, covering light years in what feels like months or even days, all while obeying the rule that nothing locally outruns light. It begins to sound like fantasy, yet the mathematics that describe such distortions are the same ones that predict black holes and gravitational waves. This is not science fiction. It is theoretical physics that has been tested again and again in other contexts. The universe already knows how to stretch and twist space. The question becomes whether intelligent life could someday learn to guide such distortions on purpose. In that possibility lies a new definition of exploration. You do not push harder, you change the path. Here lies the shimmering border between what is impossible and what is unexplored. Faster than light travel is not forbidden, it is misunderstood. We cannot break the local speed limit, but maybe we can reshape the road. We honor causality while we find clever ways to shorten the separation between places. What looks like a prison might be a puzzle instead, a puzzle built into the fabric of space-time, and puzzles are meant to be solved. The hardest part of accepting the speed limit is recognizing that the universe is not concerned with our frustrations. Light defines cause and effect, and cause and effect define reality. If a message could outrun light, reality would be free to contradict itself. You could hear the shatter of a glass before it ever slipped from your hand. You could receive a warning about an event you have not yet caused. Logic would twist into chaos. So the rule stands, protecting the order of time itself. Yet rules in nature often hide opportunities. Throughout history, boundaries that looked absolute eventually revealed secret doors. Long ago, people believed that sailing beyond the horizon meant falling into an endless abyss. The horizon was a limit carved into the imagination. Then explorers learned the horizon is simply the edge of what you can currently see, not the edge of what exists. The speed of light feels like a similar barrier. Not a prison wall, but a clue that the universe has deeper geometry waiting to be understood. When we talk about speed in ordinary life, we imagine a flat space, like a map. 1,000 kilometers per hour, 2,000 kilometers per hour. There is always more distance to cover and more speed to gain. But relativity tells us we do not live on a flat stage. Instead, we stand on a flexible tapestry that can stretch and swirl. Imagine drawing two dots on a sheet of paper and measuring the distance between them. Then imagine taking the paper and folding it so the dots touch. The dots are now neighbors. You have not increased your speed. You have changed the shape of the surface they sit on. Space is that surface. If you learn to fold it even slightly, stars that appear untouchable could suddenly become reachable. The real trick is teaching the cosmos to fold for you. In principle, strong gravitational fields already do exactly that. Near a massive object like a black hole, the curvature becomes so intense that light itself can be pulled inward, bending in dramatic arcs. Time also changes its rhythm near immense gravity. Clocks tick slower. A person close to a black hole would experience fewer moments passing than someone far away. Their time would be stretched. When they return, the rest of the universe would have aged more quickly. Travel through space can also become travel through time. General relativity gives us these extraordinary predictions, but it also gives us equations so stubborn and unforgiving that any attempt to manipulate geometry on purpose seems hopeless with our current technology. It is as though the universe has a manual with pages written in a language almost impossible to speak. Still, we know a translation exists because gravity itself reads from that manual constantly. Rockets are crude tools compared to the elegance of curvature. They burn fuel, they roar and tremble, they fight against inertia and resistance. Even the most advanced theoretical propulsion systems rely on pushing against something, whether that something is exhaust or electromagnetic radiation. Curving spacetime is different. It is not motion, but persuasion. It is asking the universe to redraw its own structure so that the destination arrives at the traveler, instead of the traveler fighting to reach the destination. The mathematics behind curved travel takes shape in a concept called a geodesic. A geodesic is the straightest possible path in curved spacetime. Light always follows geodesics because it has no mass to resist the pull of geometry. Massive objects also want to follow geodesics, but often cannot because other forces interfere. When an astronaut floats in orbit, they are following a geodesic almost perfectly, falling freely around Earth without feeling a push or pull. If you could control geodesics, you could define new pathways that take you wherever you want to go. You would no longer travel across space. Space would become the journey itself. This is why faster-than-light travel belongs not to rocket science but to gravitational engineering. It is not about speed. It is about shaping the arena in which speed is measured. Inside a cleverly curved region of spacetime, a ship could drift calmly while covering distances that would otherwise require centuries. There would be no sudden acceleration, no crushing force on the body. The ship would simply coast. Inside the vessel, all would feel normal. Outside, observers would watch a miracle disguised as a bubble of calm. It sounds almost too gentle to be real, but the same theory that predicts such quiet voyages also predicts singularities where spacetime tears apart. The peaceful warp bubble exists only because the violent black hole is possible. The equations do not promise kindness, they promise consistency. And consistency insists that if spacetime can stretch to separate stars, then spacetime can also compress to bring them close. Even now, nature reveals its power to outpace light in ways we can measure. The expansion of the universe is one example. Another is gravitational lensing, where massive galaxies bend light like giant magnifiers. Imagine standing on the edge of everything you have ever known. The space between stars stretches out farther than any road you could travel in a lifetime. Even the nearest star beyond our sun is more than 4 light years away. A light year means the distance light travels in 1 year while moving at the universe's fastest allowed speed. If our fastest spacecraft of today tried to cross that gulf, it would take tens of thousands of years. A journey longer than human civilization has even existed. It is a reminder that the cosmos is built on scales that laugh at rockets and engines and every machine we have ever made. Why is this so difficult? Why should nature care about speed at all? If we can imagine traveling faster than light, why does the universe forbid it? The answer runs deep into the foundations of reality. A century and some years ago, Albert Einstein discovered that light is not simply fast. Light defines the structure of causality. Causality simply means cause must come before effect everywhere. If something were to travel faster than light, then in certain perspectives, the effect could happen before the cause. You could send a message and receive a reply before you typed the original. Every intuition about what can happen first would collapse. To prevent logical chaos, spacetime locks the speed of causality to one specific value. That value is the speed of light in empty space. But this constant is not merely about illumination, it is about information. It is about the limit on how fast any influence can propagate. Light happens to be the thing that reaches that exact limit, because light has no rest mass. The empty space of the universe already holds the rule. You can test it with any experiment. No matter how fast you chase a ray of light, you can never gain on it. Light always rushes away with the same speed, not because it is trying to escape, but because space-time rewrites the rules of time and length around your motion To keep the limit unbroken, time itself slows for objects in rapid motion. Distances shrink in the direction of travel. Physics bends so the constraint can hold. Human instincts rebel at this idea. We think of speed as something absolute. We think if you press the accelerator harder, you should go faster. Yet relativity teaches that space and time are not a static stage where motion occurs. Instead, they are part of the performance. They transform to protect the ordering of events. When you accelerate toward the speed of light, you gain almost no extra speed. All the effort feeds instead into more energy stored in your motion. You can get arbitrarily close, but never cross the threshold. This is where our hopes seem to crumble. If no object with mass can match light, then galaxies will remain forever beyond our direct reach. We appear trapped in a local neighborhood of the universe, locked behind a cosmic border drawn by the speed of light. However, that is a misunderstanding caused by our everyday notion of distance. In the deepest description of the universe, speed is not simply about covering ground. Because space-time is curved by gravity, distances themselves can change. The geometry of the universe can stretch or compress. Two places that were once far can become close. Two events that seem separated can be bridged by bending the structure they exist within. General relativity reveals that what we call gravity is not an invisible force pulling objects. It is the curvature of space-time itself. Massive objects like planets and stars create indentations in the geometry. Lighter objects follow those curves. You feel weight because you are pushed upward by the ground while space-time tries to lead you downward along its curve. In orbit, astronauts feel weightless, not because gravity has vanished, but because they are falling freely along a curved path with no surface resisting them. The key idea is simple but profound. Nothing can locally move faster than light. Locally means within a very small region where the curvature is gentle enough to be ignored. But globally, over giant scales, space-time can evolve in ways that surpass any speed you can imagine. In the first tiny fraction of a second after the Big Bang, the entire universe expanded so quickly that distant regions raced away faster than light could ever chase. Today, we still observe distant galaxies receding from us faster than light. They are not racing through space. The space between us and them is growing. This turns the rule inside out. Light is bound to the curvature of space-time, but the curvature itself is free to do something different. That loophole forces us to rethink the meaning of travel. Perhaps the problem is not that we are too slow. Perhaps the problem is that we are trying to move through space instead of rearranging it. Picture a surfer riding a wave. The water moves, not the surfer, yet the surfer travels swiftly across the ocean. Now picture a spacecraft riding a wave of geometry. The craft rests calmly in the center, while the space behind expands and the space ahead contracts. From the pilot's view, nothing unusual happens. There is no engine pushing you, no violent acceleration. Inside the ship, you would feel as peaceful as someone sitting still. But from the outside world, your vessel would leap across immense distances, covering light years in what feels like months or even days, all while obeying the rule that nothing locally outruns light. It begins to sound like fantasy, yet the mathematics that describe such distortions are the same ones that predict black holes and gravitational waves. This is not science fiction. It is theoretical physics that has been tested again and again in other contexts. The universe already knows how to stretch and twist space. The question becomes whether intelligent life could someday learn to guide such distortions on purpose. In that possibility lies a new definition of exploration. You do not push harder, you change the path. Here lies the shimmering border between what is impossible and what is unexplored. Faster than light travel is not forbidden, it is misunderstood. We cannot break the local speed limit, but maybe we can reshape the road. We honor causality while we find clever ways to shorten the separation between places. What looks like a prison might be a puzzle instead, a puzzle built into the fabric of space-time, and puzzles are meant to be solved. The hardest part of accepting the speed limit is recognizing that the universe is not concerned with our frustrations. Light defines cause and effect define reality. If a message could outrun light, reality would be free to contradict itself. You could hear the shatter of a glass before it ever slipped from your hand. You could receive a warning about an event you have not yet caused. Logic would twist into chaos. So the rule stands, protecting the order of time itself. Yet rules in nature often hide opportunities. Throughout history, boundaries that looked absolute eventually revealed secret doors. Long ago, people believed that sailing beyond the horizon meant falling into an endless abyss. The horizon was a limit carved into the imagination. Then explorers learned the horizon is simply the edge of what you can currently see, not the edge of what exists. The speed of light feels like a similar barrier. Not a prison wall, but a clue that the universe has deeper geometry waiting to be understood. When we talk about speed in ordinary life, we imagine a flat space, like a map. 1,000 kilometers per hour, 2,000 kilometers per hour. There is always more distance to cover and more speed to gain. But relativity tells us we do not live on a flat stage. Instead, we stand on a flexible tapestry that can stretch and swirl. Imagine drawing two dots on a sheet of paper and measuring the distance between them. Then imagine taking the paper and folding it so the dots touch. The dots are now neighbors. You have not increased your speed. You have changed the shape of the surface they sit on. Space is that surface. If you learn to fold it even slightly, stars that appear untouchable could suddenly become reachable. The real trick is teaching the cosmos to fold for you. In principle, strong gravitational fields already do exactly that. Near a massive object like a black hole, the curvature becomes so intense that light itself can be pulled inward, bending in dramatic arcs. Time also changes its rhythm near immense gravity. Clocks tick slower. A person close to a black hole would experience fewer moments passing than someone far away. Their time would be stretched. When they return, the rest of the universe would have aged more quickly. Travel through space can also become travel through time. General relativity gives us these extraordinary predictions, but it also gives us equations so stubborn and unforgiving that any attempt to manipulate geometry on purpose seems hopeless with our current technology. It is as though the universe has a manual with pages written in a language almost impossible to speak. Still, we know a translation exists because gravity itself reads from that manual constantly. Rockets are crude tools compared to the elegance of curvature. They burn fuel, they roar and tremble, they fight against inertia and resistance. Even the most advanced theoretical propulsion systems rely on pushing against something, whether that something is exhaust or electromagnetic radiation. Curving spacetime is different. It is not motion, but persuasion. It is asking the universe to redraw its own structure so that the destination arrives at the traveler, instead of the traveler fighting to reach the destination. The mathematics behind curved travel takes shape in a concept called a geodesic. A geodesic is the straightest possible path in curved spacetime. Light always follows geodesics because it has no mass to resist the pull of geometry. Massive objects also want to follow geodesics, but often cannot because other forces interfere. When an astronaut floats in orbit, they are following a geodesic almost perfectly, falling freely around Earth without feeling a push or pull. If you could control geodesics, you could define new pathways that take you wherever you want to go. You would no longer travel across space. Space would become the journey itself. This is why faster-than-light travel belongs not to rocket science but to gravitational engineering. It is not about speed. It is about shaping the arena in which speed is measured. Inside a cleverly curved region of spacetime, a ship could drift calmly while covering distances that would otherwise require centuries. There would be no sudden acceleration, no crushing force on the body. The ship would simply coast. Inside the vessel, all would feel normal. Outside, observers would watch a miracle disguised as a bubble of calm. It sounds almost too gentle to be real, But the same theory that predicts such quiet voyages also predicts singularities where space-time tears apart. The peaceful warp bubble exists only because the violent black hole is possible. The equations do not promise kindness, they promise consistency. And consistency insists that if space-time can stretch to separate stars, then space-time can also compress to bring them close. Even now, nature reveals its power to outpace light in ways we can measure. The expansion of the universe is one example. Another is gravitational lensing, where massive galaxies bend light like giant magnifying glasses made of pure gravity. Photons curve around them, changing course not because they have been pushed, but because the geometry they follow has been rewritten. When we observe distant galaxies through these cosmic lenses, we are looking along a shortcut carved by gravity itself. Everywhere we look, the universe bends its shape without hesitation. It stretches at the edges faster than light can respond. It slows time near massive bodies. It sculpts the journeys of photons so subtly that stars appear duplicated or warped into arcs when seen from Earth. Gravity has always been the original architect of space-time geometry. We simply have not yet learned how to design in the same medium. To imagine controlling gravity is to imagine learning to write a new language. A language where every letter is a curve in space-time. A sentence might compress kilometers into meters. A single phrase might call distant galaxies into arm's reach. It would make the entire cosmos editable. Not a map you travel across, but a story you rewrite. Humans have always been storytellers. Perhaps someday we will tell new stories in the shape of space itself. For now, we remain at the earliest stage of curiosity. We know the rules. We sense the loopholes. We look at the speed of light, not as an unbreakable law, but as a clue pointing toward a path that does not rely on speed at all. We imagine the first device that could whisper to space-time and ask it to fold. Maybe it will begin with a tiny perturbation, a measured ripple in geometry, a controlled distortion no bigger than the width of a human hair. That might be enough to open the first doorway in a long corridor of discoveries. We will not break the speed limit. We will learn to travel without ever touching it. Every rule in physics begins as a discovery and often feels like a declaration of defeat. Heavier than air flight was said to be impossible. Then wings taught the sky a new shape. Instant communication across oceans was unimaginable. Then radio waves turned empty space into a bridge for voices. The speed of light feels like the next wall in a long line of walls. We press against it because curiosity refuses to accept distance as destiny. Still, there is humility in learning that the universe does not simply allow motion. It defines motion through the fabric of reality. When Einstein revealed that space and time are connected into a single entity called space-time, he gave us a new challenge. To travel anywhere is to negotiate with time itself. Time becomes stretchy. Hours change their pace depending on where you are and how fast you move. The faster you travel relative to someone else, the slower your internal clock becomes compared to theirs. This is not theory anymore. Astronauts aboard the International Space Station age ever so slightly less than people on Earth. Their lives stretch forward at a different rhythm because of their speed and their position in Earth's gravity. We are already time travelers, though only by fractions of a second. If time can be persuaded to slow down, what else can be convinced to shift? If distances can be altered by gravity, could they be engineered? The equations say yes. They show that space-time can curve in dramatic and surprising ways. They show that while you can never overtake a beam of light in your local surroundings, you can take a shorter path that light is not using. You can ride a different curve through the same universe. This idea reshapes how we imagine exploration. Instead of pushing a ship to move faster, we imagine asking the fabric of space to carry us. We imagine gravity not as a prison that drags us downward, but as a tool that might someday lift us upward toward the stars. Once we understand curvature well enough, we could sculpt it like a master builder. We could create hollows where travel becomes effortless. We could create channels through which our vessels glide like fish in a river. The challenge is immense. The forces needed to create noticeable distortions in space-time are usually associated with objects like stars and black holes. To replicate such power artificially seems far beyond anything within reach. But the future rarely looks possible from the present. A stone axe does not predict a lunar lander. A spark in a cave does not predict a global power grid. Our timeline of discovery is short. The universe's timeline is long. If intelligent life persists, eventually it tries everything that is not forbidden by the laws of physics. And space-time manipulation is not forbidden. A warp bubble is one such theoretical construct. In its simplest description, it would be a region of flat space-time surrounded by a shell of distorted geometry. Inside that bubble, you would float weightless. Outside, the bubble would slide across the universe as space compressed ahead and expanded behind. You would travel without moving. You would arrive far sooner than any photon traveling outside the bubble could. Yet no signal within the bubble would ever exceed the speed of light. Causality remains intact. Time remains consistent. This does not mean it is easy. It might require forms of energy that are difficult to produce or maintain. It might depend on understanding quantum behavior on a level that still hides behind mysteries. But each year brings breakthroughs. We have measured gravitational waves rippling through Earth from distant collisions between black holes. We have observed the bending of light around galaxies that existed billions of years ago. We have created tiny changes in the quantum vacuum itself in laboratory experiments. Each achievement is a step toward reading the hidden manual that governs space-time. There is a philosophical shift happening. Travel is no longer about speed alone. It is about geometry. It is about causality and how we navigate its rules. Instead of racing light, we might eventually learn to choose a different route. A route that light cannot follow because the path itself changes beneath our feet. We picture ourselves not as passengers, but as sculptors of the cosmos. When you look up at the night sky, there is a sense of unreachable beauty. Stars sparkle with a distance that feels eternal. But perhaps that emotion is temporary. Perhaps those faraway suns are closer than they appear. The darkness between worlds may be thin, like the surface of a soap bubble waiting to be poked by the first finger curious enough to test it. Curiosity is patient. It survives through doubt, through failure, through every experiment that says not yet. The speed of light is an invitation hidden as a rule. It challenges us to understand why motion has limits and how geometry might circumvent those limits. The universe has secrets. It always has. But every secret that has ever shaped history waited for someone willing to look past the apparent and study the possible. The first chapter of this story ends not with a conclusion, but with a realization. We do not have to outrun light. We can rethink what travel means. Instead of chasing the horizon, we can fold it closer. The ultimate speed limit is not the end of hope. It is the beginning of imagination. The stars are not barriers. They are destinations that physics has already placed within reach. We simply have to learn the language of space-time and speak it fluently enough to ask for the path that gets us there. Before we imagine reshaping space for our own journeys, we must confront a strange truth. The universe has already been traveling faster than light since nearly the beginning of time. Not by breaking the rule of local motion, but by bending the deeper structure beneath that rule. Gravity did this. Geometry itself did this. Nature has never been shy about outrunning photons when the situation demands it. To see this clearly, we look back to the earliest moments of existence. After the universe was born, it spent a brief instant in a state known as cosmic inflation. In far less than a fraction of a second, the size of the observable cosmos exploded from smaller than a grain of dust to something unimaginably vast. If you could have watched space undergoing inflation, you would have seen distant regions rushing away from each other at speeds that leave light hopelessly behind. But this was not motion in the usual sense. No object was racing through space. Space itself was multiplying. distances stretch so rapidly that no beam of light could have crossed even a tiny portion of what was created. This alone proves that the speed of light does not limit every form of separation. Something more fundamental is happening. The speed of light guards local cause and effect. But when the entire arena expands, the guard has no authority. In the aftermath of inflation, expansion slowed, but never stopped. Even now, the outer edges of the observable universe drift away faster than light can connect them. Light from those distant regions will never reach us. They are lost behind a cosmic boundary called the horizon. Beyond that horizon, events still unfold, galaxies still evolve, stars still burn, but their stories can never influence ours. Not because they move faster through space, but because the space between us and them grows too quickly. Gravity does not always pull things inward. On the grandest scales, it participates in the stretching of space like a silent partner guiding destiny. This expansion is not uniform everywhere. It appears linked to a mysterious form of energy woven into the vacuum itself. We call it dark energy only because we do not yet understand its nature. But whatever dark energy proves to be, it is currently pushing the universe apart faster and faster. That acceleration means that more and more galaxies will slip beyond our horizon. The sky will slowly empty over unimaginable spans of time. Light will try to chase them but never catch up. Even within more familiar realms, gravity bends what we assume is constant. Near a black hole, space-time curves so sharply that light directed outward can be bent back inward. A boundary forms called the event horizon. Nothing that falls inside can climb out. Not even a beam of light, the swiftest messenger in nature. Here, gravity does not speed things up. Instead, it slows time to a crawl. A traveler falling toward the horizon would feel nothing unusual, but an observer watching from afar would see their descent slow, then freeze, then fade. Time itself has been warped until every heartbeat near the horizon takes longer and longer compared to those outside. This is not a trick of perspective. It is a real shift in time's rhythm. It proves that space-time can stretch one person's seconds into another person's minutes. It shows that geometry controls not only distance, but also experience. Gravity writes the script for how fast time flows. We see milder versions of this even on Earth. Highly precise atomic clocks placed at different altitudes tick at slightly different rates. A clock on a mountain lives through more time than a clock at sea level. That effect is tiny, but it is enough that global positioning satellites must constantly adjust their internal timing. Without compensating for gravitational time dilation, every navigation system on Earth would drift into uselessness within hours. Our modern world runs only because we correct for the curvature of space-time. This should reshape how we think about gravity. It is not merely a force that pulls. It is a rulebook for what motion is allowed. It dictates the paths light can take. It shapes the structure of possibility itself. When gravity curves strongly enough, the allowed paths twist into shapes no intuition can predict. For example, imagine firing a beam of light past a massive galaxy cluster. Instead of traveling straight, the photons curve around the cluster in graceful arcs. Sometimes the path splits so that the same distant galaxy appears in multiple places on the sky, duplicated by nothing more than curvature. The cluster becomes a lens made of pure geometry. Observers on Earth witness scenes from deep cosmic history magnified and distorted by space-time itself. These lenses are not rare. They dot the cosmos like windows into places too far for ordinary sight. And there is a still stranger possibility. Gravity could pinch space-time so tightly that it connects distant places directly. A theoretical bridge sometimes called a wormhole. It would be a shortcut through the fabric, allowing travel between locations that would otherwise be separated by thousands or millions of years of light travel. We will explore these tunnels more deeply in later chapters. For now, It is enough to know that the mathematics of general relativity supports them. Gravity can do more than bend light or slow time. It might even fold the universe like a sheet of paper, making two remote points touch. When we see gravity behaving with such creativity, we start to understand that distance is not a fixed concept. Speed is not the whole story. The speed of light measures how fast information can move through space-time. But if space-time changes shape, that limit becomes flexible. The universe constantly reshapes itself. It stretches the void faster than any photon can chase. It traps light inside black holes. It curves trajectories into arcs and labyrinths. It experiments with geometry on scales we struggle to comprehend. This raises a profound question. If nature already breaks the rules we assumed were sacred, why should we assume those rules bind us forever? When gravity pushes galaxies apart faster than light can catch, it sends a message across the cosmos. The message says that faster-than-light behavior is not forbidden. It is simply governed by deeper principles that do not care about our engineering limitations. We stand at a point in history where we have finally measured some of these great distortions directly. Gravitational waves ripple through Earth from violent mergers of black holes and neutron stars. These waves are traveling warps in space-time itself. They stretch and squeeze everything they pass through, subtly rearranging the geometry around us. We built observatories sensitive enough to measure changes smaller than the width of a proton. That achievement proves something important. We are beginning to detect the language of gravity, and once we understand a language, we can learn to speak it. Gravity already defies every ordinary expectation. It does not merely accelerate mass, it edits distance, time, and causality when the situation demands it. Faster than light is already part of the universe's toolkit. We just have not figured out how to hold that tool in our own hands. Gravity is a master artist working with a canvas that has no edges. We think of it as weight, as the pull that keeps our feet on the ground. Yet at its core, gravity is the shape of the universe deciding how things move. When space-time bends, matter follows that bend. When time slows, clocks obey without complaint. If gravity curves sharply enough, even light, which defines the fastest possible influence, must surrender and change direction. We are used to thinking of light as unstoppable, yet gravity turns light into a dancer spinning along invisible curves. It is tempting to believe that such extreme effects belong only to faraway galaxies or monstrous black holes. But gravity shapes every second of your life. When you drop a ball and it falls, that motion is simply the ball trying to obey the natural path of space-time. The ground interrupts that journey, which is why you feel the impact. When astronauts appear to float in orbit, they are not free from gravity. They are falling. They are following the curve of space-time so perfectly that they never hit the surface below. If falling freely is following the true path of space-time, then there is a moment in science when imagination catches up to mathematics, when an idea is not merely a dream, but a logical path carved into the laws of nature. The concept of a warp drive is one such moment. It invites us to step beyond rockets and engines and think in the language of space-time itself. Not speed, not thrust, but curvature. In the year 1994, a physicist named Miguel Alcubierre studied the equations of general relativity and asked a daring question. Could space-time be shaped so that a spacecraft moves without moving? Could we create a bubble where time and distance bend in just the right way to cross unthinkable gulfs without ever nearing the speed of light? Alcubierre found a mathematical answer that astonished the world. Yes, the equations allow it. A region of space could shrink ahead of a vessel and expand behind it, creating a traveling pocket of calm in the center. The ship inside would feel no motion at all. It would float gently while the universe outside rearranged itself. That moving distortion is what we now call a warp bubble. The ship remains still relative to the bubble. The bubble travels across space-time faster than any photon outside can keep up. Yet locally, nothing violates the cosmic speed limit. It is the perfect loophole. Light defines the fastest motion through space. But warp travel does not move through space. It moves space itself. To imagine the effect, picture a table covered with a cloth. Place a toy spaceship on the cloth. Do not push the ship. Instead, pinch the cloth behind it and pull while stretching the cloth in front. The toy glides across the table without having moved relative to the cloth beneath it. The motion is an illusion from the perspective of the toy. But to an outside observer, it travels with astonishing speed. The warp bubble works this way. The ship stays seated at the heart of a stable patch of space-time, but the surrounding geometry carries it forward. Inside the bubble, time flows normally. The crew ages at its usual pace. They feel no forces because gravity and inertia are simply expressions of how geodesics shift. The bubble protects those inside from the crushing factors that ordinary acceleration would cause. No shaking, no heat, no friction. Just a quiet glide along a changed metric. The very feel of motion becomes optional, yet when the bubble arrives near its target, the tremendous journey has already been completed. This idea sounds like pure fantasy, but the equations do not lie. They are the same equations that guide planetary motion and predict the orbits of moons. They are the same equations that explain the bending of starlight and the ticking of clocks aboard satellites. The warp drive solution is drawn from mathematics that has been tested again and again. There is no violation hidden in the framework. Space-time may be more flexible than our instincts allow. The key lies in the difference between local speed and global effect. Locally, within the bubble, no part of the ship exceeds the speed of light. The speed limit remains intact. Globally, the bubble itself can reposition from one star to another as if it traveled faster than light. It is a shift in the boundary, not a sprint by the passenger. Light trapped outside the bubble cannot keep up because the distance is changing beneath it. You are not outracing photons. You are making their journey longer. Yet for all its elegance, the warp bubble comes with a steep cost. The curvature needed to produce the bubble requires a form of energy unlike anything common in nature. To contract space in front and expand space behind, the bubble must use negative energy density. That term alone sounds impossible. In everyday life, energy is positive. Fuel gives power. Light gives heat. Gravity wells are deep, not tall. But quantum mechanics reveals something stranger. The vacuum itself has fluctuations. In rare conditions, those fluctuations can be manipulated to create regions where the energy is effectively lower than zero. That is what the warp drive demands. Negative energy is not a kind of anti-fuel. It is a property of space-time that resists the usual push of gravity. Where positive energy curves space inward, negative energy curves it outward. To keep the bubble shaped correctly, one must balance these curvatures in a delicate dance. A ring of negative energy around the bubble holds its form. Without such a ring, the entire structure collapses and the journey ends before it begins. Alcubierre did not build a ship. He drew a map, a mathematical route through the deepest rules of the universe, a route that promises shortcuts longer than any straight line. But the map demands resources that seem far beyond our capability. The amount of negative energy required in the original design was immense, more than the energy content of many stars combined. Later refinements reduced the requirement, but did not remove the challenge. We may need a breakthrough in quantum technology, or a new understanding of vacuum structure to generate such exotic conditions. Still, the idea stands untouched by contradiction. It reveals a truth many feared was forbidden. The universe does allow effective faster-than-light travel, as long as we define travel not as motion relative to space, but as alteration of the space itself. The ship never rushes. The distance simply yields. In imagining this future, one must picture a vessel sailing across space-time without thrust. Silent, graceful, carried by geometry. It would have no need to fight resistance or burn colossal amounts of fuel. It would no longer trade energy for speed. Instead, it would trade understanding for access. Knowledge of curvature becomes the engine. The equations become the sails. There is something poetic in the idea that if we want to reach the stars, we must learn to speak the same mathematical language that stars and gravity already speak fluently. We must treat space-time not as a mere backdrop, but as the medium of travel itself. Every great leap in exploration has come from learning a hidden rule. The warp drive might be the greatest hidden rule of all, but the universe has never given away its secrets easily. Every solution in physics carries consequences. The warp bubble is no exception. It leads us to questions that reach the limits of understanding. Questions about energy, stability, and causality. Questions about whether such travel would tear holes in the cosmic order rather than simply bending it. We are still at the beginning of this thought. The mathematics opens a door, but beyond that door lies a frontier that demands caution as much as it demands wonder. What Alcubierre taught the world was not how to build a warp drive. It was how to think about travel differently. We are not shackled to the speed of light. We are shackled to our assumptions about what travel means. There may be a future in which we glide among the stars, not by conquering the void, but by persuading it to help. The warp drive idea marks the moment when faster-than-light exploration transitions from myth to mathematics, from impossibility to possibility, from a distant hope to a well-defined solution waiting for the technology to catch up. And even though that technology may be centuries away, the story has already changed. The warp bubble is unlike any propulsion system we have ever imagined. Ordinary engines push against something. Rockets shove exhaust backward and drift forward by reaction. Even ion thrusters, the most efficient engines currently flying in space, still depend on ejecting particles. Every form of thrust demands a trade. You feed energy into motion, and the more speed you want, the more fuel you must spend. The rocket equation rises like a mountain in front of any dream of interstellar travel. It punishes ambition with exponential obstacles. Warp travel has no such equation. There is no exchange of mass for speed, because there is no speed in the usual sense. The spacecraft remains almost motionless inside its cocoon of flat space-time. The bubble around it does the work. From the perspective of those inside, they drift with total calm. No burning engines, no screaming vibrations, no fear that every new meter per second requires costs that eventually become absurd. The bubble is like a pocket carried along by the tides of geometry. This calm interior is one of the most extraordinary features of the concept. In conventional acceleration, approaching the speed of light would crush you under monstrous forces. Your body could not withstand what the mathematics demands, but in a warp bubble, passengers feel nothing. There is no acceleration to resist. There is no drag from particles in space. The travelers could sip tea as they cross the width of a galaxy faster than any photon can keep up. A journey that would take millions of years for light could become a voyage measured in days if space-time itself changes the separation. This is why the warp drive solution was so shocking. All the major rules of special relativity remain respected. No particle outraces a photon through the space next to it. No information inside the bubble travels faster than the speed of light. The mathematical guardrails stay upright. Yet the shift in perspective is profound. To understand warp travel is to accept that motion is not the only way to reach another place. It is important to recognize what the warp bubble does not do. It does not shorten the entire universe. It creates a controlled region of distortion that glides through the cosmos. Without that controlled shape, the bubble would collapse. Without the precise balance of curvature, the geometry would pinch or tear. The ship inside would not be harmed, but the journey would end. Stabilizing the distortion is the true test of engineering. Some version of a gravitational field must be sculpted around the vessel with astonishing precision. To hold the bubble steady, You need a ring of matter or energy that curves space-time outward instead of inward. This is where the idea reaches the edge of our understanding. Positive energy always curves space inward. That is why mass attracts. To curve space outward, we require negative energy density. That idea is not science fiction. It exists in proven physical effects, such as the vacuum fluctuations studied in quantum field theory. When two mirrors are placed extremely close together in empty space, the quantum vacuum between them changes. The result is a measurable force drawing the mirrors together. That phenomenon is called the Casimir effect. It demonstrates that there are ways to manipulate vacuum energy. And with the right configuration, regions with lower than zero effective energy can appear. However, the amount of negative energy produced by the Casimir effect is minuscule, far too small to shape a bubble large enough to carry a ship. It is a whisper when the warp drive demands a thunderclap. Some physicists doubt that enough negative energy can ever be gathered. Others suggest that a future understanding of quantum gravity may reveal new methods. Perhaps dark energy itself could be harnessed one day, or perhaps exotic phases of matter discovered in extreme environments could supply the needed properties. Even with unlimited negative energy, another challenge arises. The bubble must be built before it moves. You cannot form a warp bubble around a ship using signals from inside, because those signals cannot outrun the boundary they are trying to create. To ignite the bubble, you might need external machinery capable of arranging space-time on a grand scale. A network of devices shaping a corridor of geometry before a ship departs. We do not yet know whether such coordination could ever be practical. The mathematics also warns us that a warp bubble may create a wake of radiation. As it moves, stray particles could accumulate at the front edge of the bubble. When the bubble comes to a stop, that trapped energy might be released. In a blast, the arrival point could experience a burst of high-energy radiation. Engineers of the future will need to tame this hazard or redesign the bubble to prevent such buildup. Yet none of these obstacles invalidate the idea. They simply mark the frontier. They highlight the gulf between what is mathematically allowed and what is technologically possible today. Humanity does not currently have the tools or materials to build a warp drive, but the concept has already changed the conversation. It proves that faster-than-light journeys do not violate physics if we redefine what a journey is. Alcubierre's discovery created a map where once there was only a blank space labeled impossible. Perhaps the true significance of the warp bubble is inspiration. A clear demonstration that the laws of nature do not crush every bold imagination. Instead, they offer challenges written in equations, waiting for curious minds to decode them. As we study the warp drive, we learn not only about future propulsion, but about the deep structure of reality. We begin to view gravity not as a barrier, but as an ally. We begin to picture space-time not as a cage, but as a craftable medium. We begin to see exploration not in terms of speed, but in terms of geometry. The story of the warp drive is the story of how physics expands possibility. It reminds us that every distance is a relationship between places, and relationships can change. There is another twist that emerges the deeper we explore warp travel. If a bubble of distorted space-time can move faster than light relative to the outside universe, then it might also create the potential for strange loops in causality. Some solutions allow a bubble to leave and return before it departed from the perspective of certain observers. Time would become flexible in a way that invites paradox. Could a traveler reach a destination before the signal announcing their arrival? Could a message interfere with its own origin? These puzzles remind us that mathematics can be clear while consequences remain unclear. Physics protects logic fiercely. When contradictions appear, we suspect that important details are still missing. Many physicists believe that quantum effects may impose hidden boundaries that prevent warp bubbles from creating causality violations. Others propose that as soon as any geometry threatens a paradox, nature simply refuses to let it remain stable. This idea echoes a principle known as chronology protection. The universe does not allow time to twist itself into knots. If the warp bubble is to become more than a mathematical curiosity, these protections must be understood and respected. We would seek design choices that allow incredible travel without inviting impossible timelines. Even with such challenges, the warp drive remains a landmark idea because it shifts our thinking from propulsion to geometry. Rockets scream against inertia. Warp bubbles ask space-time to do the work. Instead of hurling ourselves across the universe, we let the universe close the gap. That difference changes everything about how we imagine the future. No fuel tanks the size of skyscrapers. No decades spent coasting through cold emptiness while generations live and die aboard a ship. Travel becomes an act of shaping reality rather than fighting it. There is a quiet beauty in the notion that the ship itself rests while the cosmos flows. Imagine floating inside a bubble where the stars arrange themselves into a changing mural outside the window. Time passes gently. Space ripples slowly. The bubble glides with effortless grace. Inside you might read a book or look out into the velvet expanse, forgetting that trillions upon trillions of kilometers are slipping by. Then the distortion ends. The bubble dissolves. The new star is now a sun in your sky. It is difficult to overstate how radical this would be for civilization. The barriers between worlds would melt. Exploration would become migration. The borders of possibility would expand until the galaxy feels like a neighborhood. Humanity could visit planets that have only ever been specks of light. Entire new histories could unfold as life crosses distances that once felt eternal. The concept of isolated existence would fade into myth, but wonder must always walk beside caution. Until we understand the exact behavior of negative energy, we cannot know whether a stable warp bubble can last longer than a moment. The region of distortion must remain smooth and free from abrupt changes that might tear the bubble apart. Stability is a strict requirement. A warp drive fails no less completely than a rocket if it collapses mid-journey. Unlike a rocket, the collapse may cause sudden reconnection with ordinary space at enormous speed, releasing energy in unpredictable ways. The careful balancing of curvatures also demands a structure around the bubble. A ring-shaped distribution of exotic energy is a common feature in the theoretical models. It must be shaped precisely. If the ring drifts or distorts, the bubble could tilt or rotate. Navigation might require guiding this gravitational architecture like the rudder of a ship. Steering would not involve thrusters. It would involve adjusting curvature. This new mode of travel would demand a new mode of thought. Pilots would become sculptors of geometry. Engineers would become designers of space itself. Astronomers would not merely observe distant stars. They would plot paths through the fabric that connects those stars to home. A warp ship captain would not speak of speed. They would speak of alignment. They would speak of curvature fields and the gentle art of bending the universe just enough to stay on course. Even with all uncertainties, one truth remains solid. The warp drive is not fantasy because the mathematics of space-time allows it. The primary barriers are practical, not theoretical, and practicality evolves. Human history is filled with inventions that once seemed absurd. The first time someone suggested sending a voice across the ocean through empty air, it sounded like magic. The first time someone imagined flying above the clouds, it sounded like myth. The first time someone imagined reaching the moon, it sounded like a story for children. Then each dream became a new chapter of reality. The warp drive may take centuries. It may demand breakthroughs in quantum engineering that transform technology from the ground up. But the door is not closed. It is open just wide enough to see the glow of possibility on the other side. That glow is enough to guide curiosity, enough to justify research, enough to tell us that humanity has not reached the limit of its reach. In the end, the warp drive teaches a profound lesson. We do not conquer the universe by force. We learn to travel by listening to its rules. The universe already knows how to move faster than light. It stretches itself. It curves. It bends. It builds highways in geometry that photons cannot follow. One day, Guided by knowledge and courage, we might step onto those highways. The warp bubble is a promise written in equations, a promise that distance can be tamed, that time can be kind, that the stars are not as far as they seem. There are ideas in physics that make us excited. There are ideas that make us cautious. And then, there are ideas that do both at once. Negative energy belongs to that final category. It is the kind of concept that forces us to ask whether the universe has hidden regions of possibility that we are only beginning to glimpse. It is also the kind of concept that warns us nature will not grant such power lightly. Everything familiar in life has positive energy. When you lift an object, you give it gravitational potential energy. When a star burns nuclear fuel, it releases radiant energy. Even the heat inside your body is a store of positive energy. That is why gravity pulls rather than pushes. Matter of any kind bends space-time inward, creating the curves we experience as attraction. Positive energy always makes geometry descend. But for a warp bubble to form, space-time must curve outward around its rim. It must create a kind of hill in geometry rather than a valley. That requirement demands something far stranger than ordinary matter, something that resists gravity instead of obeying it. In the equations, this is achieved by negative energy density. When that term first appears, it sounds like fiction. How could energy be less than zero? How could the universe allow a deficit so deep that even the vacuum itself seems rich by comparison? Yet quantum mechanics teaches that empty space is never truly empty. The vacuum is a restless sea of fluctuations where particles appear and disappear too quickly to be detected directly. This jittering of existence is subtle but measurable. It affects how atoms behave. It generates tiny forces that would not exist if emptiness were truly empty. And under very precise conditions, those fluctuations can be manipulated so that the energy in a region slips below ordinary emptiness. That is negative energy density in the most basic sense we currently understand. One of the clearest demonstrations of this strange effect is called the Casimir effect. Imagine placing two smooth metallic plates parallel to each other, separated by a very tiny gap. The vacuum inside that narrow space is not the same as the vacuum outside. Only certain quantum waves fit perfectly between the plates. Some of the usual fluctuations are excluded. That exclusion reduces the vacuum energy between the plates. Suddenly, there is slightly less energy in the gap than around it. The result is a gentle but measurable attraction that pushes the plates toward each other. Two surfaces drifting together powered by the quiet subtraction of energy from emptiness itself. The Casimir force is tiny. It becomes noticeable only when the plates are placed extremely close together. The negative energy produced is minuscule, not even enough to influence a dust grain floating in the air. But that demonstration is proof of principle. It tells us the vacuum can be sculpted. It tells us space-time responds to subtle changes in the energy field woven through it. It tells us that negative energy is not a fantasy. It is written into the equations and confirmed by experiment. Why is this so important for warp travel? Because the warp bubble needs regions of space curved outward precisely by negative energy. It is the ring around the bubble that must carry this unusual property. Without that ring, space-time collapses inward, as it always prefers to do. The bubble would fail. The center of calm would vanish, and our vessel would return to ordinary physical reality and ordinary speed very quickly. So the warp drive depends not on brute strength, but on a subtle twist in the deepest laws of nature. It asks us to master the vacuum itself, not the cold void between stars, but the quantum storm that never truly quiets. It asks us to generate negative energy in amounts and shapes far beyond what the Casimir effect currently offers. Physicists have studied the conditions under which negative energy can appear. The lessons are difficult. The universe allows such energy, but only in strict and delicate arrangements. You cannot simply gather vast pools of negative energy like fuel. nature applies what are called quantum inequalities. They limit how much negative energy can exist in a region and for how long. A pulse of negative energy must be brief. A deep dip below zero must be accompanied by nearby peaks above zero. The vacuum demands balance. When one side of the ledger goes negative, the other must compensate to keep the entire sheet in cosmic order. These constraints make negative energy both precious and fleeting. It is as though nature allows us a glimpse of forbidden power, then slams the door before we can seize more than a handful. It is reasonable to wonder whether these limitations permanently prevent warp travel. Some scientists believe that is likely. Others argue that we have only seen the simplest forms of negative energy. More advanced configurations may relax the bound. The vacuum might offer loopholes that have not yet been noticed. For thousands of years, electricity was just lightning in the sky. That did not stop us from harnessing it. Negative energy might also be waiting for a clever breakthrough. Dark energy complicates the mystery further. This unknown pressure drives the acceleration of the universe's expansion. It behaves in some ways like negative gravity. It pushes space outward. Some think it could be a large-scale cousin of negative energy. If humanity ever identifies and controls dark energy, it might become the ultimate resource for curvature engineering, though that dream remains as distant as the stars we hope to reach. Imagining negative energy is like imagining a currency that does not follow ordinary rules. Positive energy buys motion. Negative energy buys geometry. Positive energy fuels stars. Negative energy may one day fuel starships. It could become the ticket to bending space-time on command. But like any valuable currency, it comes with risks. The same physics that can hold open a warp bubble could destabilize a region of space if misused. The exotic fields required are sensitive. A miscalculation might shred the bubble or tear a tiny ripple in causality itself. This is why negative energy is described as dangerous, not because it explodes or burns, but because it can coax reality into shapes that threaten logic if handled carelessly. Those who wield such power must understand every wrinkle in every equation. They must sculpt curvature with respect for the order that holds the cosmos together. They must treat geometry as a living system that cannot be violated without cost. What matters, though, is possibility. We know negative energy exists in principle. We know the warp drive needs it. We know nature allows it in small doses. We do not yet know whether nature will permit its use in the heroic quantities required for travel among the stars. That unanswered question defines the horizon of gravitational engineering. The warp bubble showed us the destination. Negative energy reveals the price, and the price is steep because the reward is profound. Faster than light travel. A universe without unreachable places. That is worth searching for. Negative energy invites ambition, but it also forces humility. The universe is clever in the ways it protects itself. When we try to push space-time into unfamiliar shapes, the equations push back. They insist that every unusual bend must be countered by something ordinary nearby. They insist that every escape from gravity's grip must be compensated by a stronger pull in the same neighborhood. It is as if nature allows us to borrow geometric freedom only if we promise to repay it soon after. We are permitted a moment of rebellion against the usual curve of space, but never a permanent victory without consequence. This balance shows itself clearly in the strange rules known as quantum energy inequalities. These inequalities state that if negative energy appears in one region, positive energy must gather around it, either before or after, or both. The deeper the drop below zero, the shorter the time allowed. The longer the negative energy persists, the shallower the dip must be. The vacuum behaves like a strict banker holding accounts in perfect cosmic bookkeeping. It never forgets a debt. For a warp bubble, the dream is to maintain a ring of negative energy long enough to travel while minimizing the compensating burst of overwhelming positive energy. Because that positive energy could collapse the bubble, or worse, collapse the geometry inside. The trick is to distribute negative energy smoothly so the pressure of repayment is spread across space and time without violent consequence. But we do not yet know how to do this. The calculations are unforgiving. They show that even tiny instabilities can distort the bubble into collapse or stretch the shape into dangerous patterns. This brings us to another difficulty. Negative energy is naturally fragile. It hides within delicate quantum effects that falter when disturbed. The moment we expose it to heat, motion, or any significant interaction, the vacuum tends to restore itself to a comfortable state of positive energy. It is like trying to hold water in a net. The slightest mistake, and the exotic quality slips away. The engineers of a future warp vessel would require a new type of technology. Devices that manipulate quantum vacuum fields with precision at scales far beyond current capability. They would need to shape and contain negative energy without letting ordinary energy flood in to destroy the configuration. They would need materials that guide curvature, forms of matter that do not buckle under contradictory forces. Perhaps matter with strange quantum symmetries that allow stability where none should exist. We cannot yet imagine the full design, but we can imagine the challenge. It may sound intimidating, yet every major scientific transformation in history once sounded the same. The first person who thought of controlling electricity did not know what a battery would look like. The first astronomer who dreamed of measuring distant galaxies did not know how a telescope would focus light. We always invent the tools after we understand the need. Negative energy represents both the need and the tool. We have identified one of the keys. We simply do not yet know how to hold it. Another mystery deepens our curiosity. Negative energy does not only appear in laboratory plates, it may appear near the surface of black holes where space-time is stretched to breaking. Stephen Hawking predicted that black holes radiate energy slowly over time. That radiation, called Hawking radiation, draws energy from the black hole itself. According to the theory, virtual particle pairs appear near the horizon. One falls inward, the other escapes. The one that falls inward may carry negative energy, allowing the black hole to give up mass. If this picture is correct, then the universe naturally generates negative energy near the most extreme gravitational objects. Black holes might be factories where space-time continuously produces the exotic ingredient required for warp travel. We cannot collect such energy yet. We cannot go near a black hole safely. But the existence of negative energy in nature tells us that the universe does not forbid it. The door is unlocked. We have only to build the hand capable of turning the knob. Some researchers wonder whether negative energy could be enhanced by quantum information technologies. Entanglement allows correlations between particles across distance. Could those correlations be shaped to produce negative energy fields? Could the whisper of information traveling through the quantum foam stabilize the bubble's exotic structure? These are questions for the next century of physics, perhaps even the next millennium. But questions worth asking do not fade simply because the answers lie far ahead. There is also the possibility that negative energy can be created indirectly by manipulating strong electromagnetic fields. Some theoretical studies suggest that the vacuum responds to intense electric and magnetic intensities in ways that temporarily lower local energy density. High-energy lasers and superconducting coils may one day reveal pathways to amplifying these distortions. We might eventually weave networks of machinery that push space-time in opposite directions, forming ripples that align into a stable curvature pattern. Every ripple begins as a gentle wave, but under the right harmony, waves become a sculptor's chisel. We must also address fear. When people hear that negative energy can in theory oppose gravity, some imagine a path to destruction. They worry that such power could rip space-time apart, tear holes that unleash unstoppable consequences. The truth is more controlled. Negative energy is not a weapon by nature. It is a tool that must obey the strict constraints of quantum law. The vacuum will not allow reckless manipulation. It fights back whenever its balance is threatened. Harnessing negative energy would require careful respect for the structure of reality. It is a challenge that demands wisdom before ambition. Still, the potential reward is profound. If negative energy can be shaped and sustained, the warp bubble becomes more than a mathematical solution. It becomes engineering. It becomes transportation. It becomes a method for exploring worlds that have remained nothing more than faint glimmers in the night sky. It brings us to the threshold of a future where distance is no longer a wall, but a suggestion. Negative energy is the cost of admission to that future. It is the rare currency that buys a change in geometry, and geometry is the true language of faster-than-light travel. We stand at the beginning of this story with only hints and whispers to guide us, but every step forward reveals a wider field of view. A century from now, the idea of bending the vacuum may seem no stranger than flying once seemed to the ancestors who stared up at birds and wondered what held them aloft. Negative energy challenges the imagination in another subtle way. Most of what we know in physics starts from things we can touch or at least measure directly. Heat, motion, radiation, mass. These are familiar pillars. Negative energy instead belongs to the background fabric that quietly supports everything else. It does not push in the conventional sense. It bends. It reshapes what is allowed. It makes certain curves of space-time easier or harder to form. It is a sculptor's influence rather than a soldier's force. To work with negative energy, we are learning to think like space-time itself. That means accepting that distance and duration are not fixed objects, but flexible properties. When we speak of changing distance, we often imagine compressing matter or sliding objects closer together. But a warp bubble does not change matter. It changes the meaning of distance. Two stars separated by a stretch of space might suddenly find that stretch shortened if the geometry connecting them is altered. That change requires a region of space-time whose curvature bends outward, and that outward curvature is powered by negative energy. To picture this, imagine placing a heavy ball on a soft membrane. The surface dips under the ball. That dip is what positive energy does. Now imagine lifting the membrane upward into a gentle dome instead. That dome is what negative energy would create. A warp bubble combines domes and dips into a controlled pattern. It lifts in some areas and sinks in others, forming a traveling pocket of neutral flatness inside. The ship rides in that flat region, while the surrounding geometry shifts the universe beneath it. From inside the bubble, passengers see the stars change position rapidly, yet feel as if they drift without motion. This is crucial. In the bubble, time flows evenly. No dangerous acceleration affects the body. No aging discrepancy steals decades from the crew. They live each moment without sacrifice, while the universe rearranges the road before them. This peaceful ride is not a side effect, it is the point. The universe allows motion beyond light speed only when motion ceases to be motion in the ordinary sense. The ship does not race, the ship persuades. But persuasion comes with constraints. Negative energy is rare because geometry fights the unnatural. The universe prefers to curve inward. The surface of space-time resists any attempt to expand outward like skin resisting a stretch. What expands must be fed with energy that disagrees with how matter normally warps the cosmos. You must supply not only the exotic negative energy, but also maintain its shape in a delicate balance. The bubble must stay smooth. A wrinkle might tear the curvature. A tear might unravel the entire structure. Even if we learn to create negative energy, we must learn to guide it. A future warp vessel would require constant recalibration, adjusting the distribution of energy to counter disturbances. Space is not empty. Stray particles, radiation, and interstellar gas could bump against the bubble. The geometry might wobble. Navigation would be as much about protecting the bubble's symmetry as about choosing direction. Instead of steering through space, pilots would steer the bubble's curvature. Add to this another complication. While negative energy curves space outward, The concentration of positive energy that must accompany it might affect time in unpredictable ways. If the positive energy becomes too dense in certain regions, time dilation could grow extreme. It might stretch seconds into long pauses or compress moments into blinks of rapid change. The safest bubble is one in which these effects remain even and gentle across the boundaries. Some theoretical studies suggest a warp bubble might require continuous monitoring of the external geometry using sensors that record tiny fluctuations in curvature. The ship might carry fields of reference particles that trace the shape of space just outside the bubble, like dust tracing the wind. Computers would interpret those patterns and adjust the negative energy distribution to keep the bubble stable. It would be like balancing a marble on a sheet of silk during an earthquake, yet done with mathematical elegance rather than brute strength. Difficult? Yes. Too difficult. We cannot say that. The universe rarely hands out easy rewards when the prize is cosmic freedom. It makes us prove that we are ready. It makes us learn stretching the vacuum without ripping the threads. It makes us master geometry as deeply as we mastered fire and electricity. The first explorers who learned to navigate oceans with nothing but stars and courage had no guarantee of return. The first builders who imagined flying through the air had no promise that wings would carry them. Challenge does not mean impossibility, it means importance. Negative energy is a tool that can inspire or intimidate depending on how we approach it. If we fear every unknown, we remain standing on one small world looking outward for eternity. If we proceed with caution and curiosity together, we build ships that cross oceans of starlight. The unknown becomes the birthplace of discovery. Perhaps the most powerful idea hidden in negative energy is the reminder that emptiness itself holds potential. All around us, space seems quiet and still, but beneath that quiet is a swirling foundation that defines everything. Matter floats on a sea of fluctuations. Geometry rests upon a restless storm. If we learn to speak to that storm, we can navigate the universe in ways no one today has ever experienced. The warp bubble is the dream. Negative energy is the cost. This currency is rare, expensive, and dangerous to mishandle. But if we learn to earn and spend it wisely, distance will lose its power over us. The stars will open like pages in a book. There is one more truth about negative energy that matters deeply. The same exotic substance that could enable warp travel could also hold open a gateway between distant places. That gateway is a wormhole, and wormholes take the idea of bending space to its ultimate conclusion. A wormhole is the boldest suggestion that nature ever whispered into the equations of general relativity. It tells us that space need not be a smooth, unbroken expanse, stretching endlessly in every direction. Instead, it might contain shortcuts, tunnels, hidden bridges that tie distant places together so tightly that the journey between them becomes almost instant. A wormhole is a fold in the grand fabric. Two distant stars could in truth be neighbors if the fold is shaped correctly. To understand how strange and exciting this is, we must first picture space-time as more than emptiness. Imagine the cosmos as a vast blanket. Every star and planet presses down into that blanket, forming curves that guide motion. A wormhole adds a twist. Instead of a simple dip where space-time bends inward, a wormhole connects two such dips with a throat. Fall into one side and you emerge from the other, without ever crossing the ordinary distance in between. It is like slipping through a secret hallway that ignores the usual map. Einstein himself glimpsed this possibility when he studied strong curvature. Alongside Nathan Rosen, he described what is now called an Einstein-Rosen bridge. It appeared naturally in the mathematics that describes a non-rotating black hole. In that solution, the geometry suggests two separate regions of space joined at the event horizon by a bridge. But that bridge snaps shut so quickly that nothing can cross it. The throat connects worlds only for an instant before collapsing. There is no time for a traveler to pass through. That first vision of a wormhole was a promise without a doorway. Later, physicists wondered whether the bridge could be held open. The answer returned by the equations was yes, but with a catch that echoes the warp drive itself. To keep a wormhole from collapsing, you must support the throat with negative energy. Normal matter wants to crush the opening like a clenched fist. Only exotic matter with the reverse gravitational effect can hold the structure open. The same strange currency required to power a warp bubble is required again here. Negative energy is the key to unlocking almost every gravitational shortcut. If it can be controlled, a wormhole would make distance irrelevant. A trip from Earth to a world near Alpha Centauri could take minutes instead of years. Journeys that currently need generations could become afternoon excursions. The entire galaxy might shrink to the size of a neighborhood. The gulf between stars would become a hallway. The idea is intoxicating. It offers freedom from the cruel separation that has defined human life since the first time we looked up at the night sky. Yet wormholes come with challenges that rival their allure. Stability is the first. Space-time hates to be twisted into sharp shapes. The throat of a wormhole wants to pinch closed almost immediately. Negative energy must act as a brace. Without enough exotic material, the walls collapse faster than any traveler can move. Worse still, the collapse might trap anything inside, leaving it lost forever in a region that no longer connects to any known place. Engineers of a future civilization would need to keep the geometry smooth and perfectly balanced, funneling just the right distribution of negative energy along the throat. Then comes another problem: causality. A wormhole connects 2 points, not only in space, but in time. If one end moves, then its relationship to time shifts. If you accelerate one mouth of a wormhole near light speed or bring it close to a strong gravitational field, time moves differently for that mouth compared to the other. When you reunite the two ends, you have created a time shift. A traveler could step into one end and emerge before they left. That sounds like victory over distance, but it also sounds like trouble. If messages can be sent into the past, paradoxes threaten to appear. Could someone destroy the cause of their own journey? Could information circle endlessly with no origin? These puzzles suggest that nature may enforce rules that prevent wormholes from enabling unrestricted time travel. Some theorists believe that quantum effects would flood a wormhole with energy the moment it attempts to form a paradox, sealing it shut to protect causality. Others think wormholes might remain open, but resist configurations that create contradictions. The universe can be playful, but not self-defeating. It allows creativity only within a framework that keeps logic intact. If wormholes exist, they likely obey this deeper order. We must also ask where a wormhole leads. The simplest version links two distant points in the same universe, but there are solutions that hint at other possibilities. Some geometries resemble tunnels to entirely separate regions of space-time, perhaps even other universes. If so, the first explorers to cross such a bridge would face uncertainty greater than any sailor crossing an ocean. What awaits on the other side might not be a familiar star or familiar physics. It might be something new entirely. There is reason to suspect wormholes might form naturally in regions where quantum foam churns wildly at the smallest scales. At distances far smaller than atoms, space-time might not be smooth. It might froth like boiling water. Tiny wormholes could appear and vanish constantly. They would be far too small for travel, but they would hint that the underlying fabric welcomes connection. If intelligence someday learns how to stabilize and stretch one of those microscopic tunnels, then cosmic travel would become a matter of engineering rather than dreaming. Wormholes are not yet observed. We have not seen a star twisted into arcs that suggest a hidden tunnel. We have not detected gravitational signals that match the signature of a throat opening between worlds. But we have also only just begun to see the universe with the tools required. Gravitational wave observatories and next-generation telescopes may someday find the first evidence that space-time holds doors. And the moment such a door is seen, the race to understand and eventually use it will begin. Despite the obstacles, the potential rewards are immense. A wormhole does not simply shorten travel, it changes the nature of existence. Isolation ends, exploration becomes effortless. The human story expands beyond one star system into thousands. A network of wormholes could tie planets into a web of swift passage where knowledge and culture flow freely. Civilizations could cooperate on scales that are now unimaginable. The night sky would no longer be a distant spectacle, but a map of reachable worlds. There is poetry in imagining two lovers, separated by light years, stepping through a wormhole to share a single sunset. There is power in imagining scientists working together while orbiting completely different suns. There is profound hope in imagining that life scattered across the galaxy could grow connected rather than alone. This vision depends on mastering geometry. It depends on taming negative energy. It depends on respecting causality while finding safe paths through the deeper layers of space-time. The technology remains far beyond us, but the mathematics sits on the table waiting to be read more deeply. Wormholes remind us that the universe is not static. It is playful and clever and filled with possibilities that surprised even Einstein. If we learn how to keep a throat open safely, if we learn how to shape the vacuum into the supporting ring needed for stability, if we learn how to avoid paradoxes while traveling through that secret channel, then the dream becomes real, and distance becomes gentle. Wormholes are gravity's secret doors. Nature has already hinted that it knows how to build them. We only need to learn the craft. Gravity has always been our first partner in space travel. Long before we imagined warp bubbles or wormholes, we learned that a clever dance around a planet could give a spacecraft more speed than its engines could ever provide. This maneuver is called a gravitational slingshot. A tiny probe like Voyager, riding the curve of Jupiter, gained enough momentum to flee the entire solar system. It was not pushing harder. It was stealing a little energy from a giant world. Gravity lent a hand, allowing a fragile machine to reach the stars. The idea is simple, but profound. When a spacecraft falls toward a planet, it accelerates. If it swings around the world at just the right angle, it can depart with more speed than it arrived. It borrows a tiny amount of the planet's enormous orbital energy around the Sun. The planet slows down a nearly invisible amount, while the spacecraft gains a massive boost. That exchange reminds us that gravity is not merely a pull downward. It is a tool for navigation through the curves of space-time. This trick works because motion is relative. The planet is moving fast around the Sun, and the spacecraft can take advantage of that motion. The path bends around a well of curvature and emerges with a new trajectory. For missions within the solar system, slingshots are a method to cheat the rocket equation. They let explorers go farther with less fuel. They show that when geometry offers a slope, you do not have to climb it. You can slide. On a larger scale, gravity offers tricks far stranger than slingshots. Time itself becomes a navigational variable. A clock on Earth ticks faster than a clock deep in the gravitational field of Jupiter. A clock in orbit ticks faster still because it is farther from the center of mass. These tiny differences matter. Our positioning satellites adjust their internal timing constantly because the geometry of time bends under the influence of mass. Without those adjustments, every global navigation device would drift into useless guesses. The rhythms of time are instruments that must be tuned to gravity's song. If astronauts venture close to a neutron star or a black hole, the effect becomes dramatic. A traveler near the surface of a neutron star could experience 1 hour while years pass for those far away. Time dilates not because of speed, but because gravity stretches the very meaning of a moment. If a trip near such an object is planned carefully, the traveler might shorten the journey by letting the outside universe rush forward. They would move less in space, but more in time. Upon returning, they would find that others have completed most of the waiting for them. This is not exactly faster than light travel. It is faster arrival. The destination still lies across space, but the timeline shifts in your favor. Gravity offers a shortcut through time rather than distance. In extreme cases, this becomes nearly as powerful as bending space. Imagine a journey that takes 1 year aboard the ship, but 1,000 years outside. To the travelers, it is quick. To those waiting, it is long. But that difference could allow a civilization to leap far across the galaxy using time dilation as its ally. There is a subtle elegance in the way gravity sculpts both space and time. A spacecraft does not have to outrun light. It only needs to choose paths where light takes longer. A nearly circular orbit around a heavy object can become a long fall into slower time. A daring swing past the edge of a deep curvature can give you more future than distance would normally allow. Navigation becomes choreography. The ship is a dancer following the curves nature provides. Gravitational waves add a new layer to the dance. When massive objects like black holes collide, they send ripples through the geometry of the cosmos. Those ripples carry energy across immeasurable distances. We have detected them on Earth, stretching and compressing every atom they pass through by an amount smaller than a single proton. Space is not silent. It vibrates. In theory, a craft could surf a gravitational wave the same way a surfer rides a moving swell of water. If you catch the wave correctly, you are carried as space itself moves. We are nowhere near this level of mastery. Our measurements barely capture a whisper of gravitational change. But the fact that these waves exist and propagate means that space-time can transmit motion without matter. A voyager who learns to align perfectly with such waves may ride them across light years with no engines at all. It is a theoretical path that sounds like fantasy until you remember that we already listen to these waves in our laboratories. Artificial gravity manipulation remains a dream. We cannot yet produce noticeable curvature. But imagine a future in which devices create controlled wells or hills of space-time. A ship could hop from one curve to the next, propelled not by thrust, but by falling through geometry. Distance would become a series of gentle plunges guided by precision. Fuel would power the bending of geometry rather than the expulsion of mass. One may ask what happens to the laws of motion in such travel. The answer is simple. They remain intact. You are always falling. You are always following the shape carved into space-time. The trick is to put the right shapes in the right places. A corridor of curves that lead exactly where you want to go. In a way, this focus on gravity is more grounded than the wild leaps of warp bubbles or wormholes. We already use gravity to travel. We already correct for time dilation. We already measure gravitational waves. These are not distant theories. They are working parts of our spacefaring life. To extend this approach into advanced propulsion is not to abandon known physics. It is to adopt it more fully. There is a quiet message hidden in every gravitational slingshot. Nature wants us to use geometry. It rewards clever paths. It punishes brute force. The most efficient voyages are not the fastest engines, but the smartest arcs. The universe invites us to glide, not struggle. One day, ships may roam the galaxy powered by gravity itself. They will not roar. They will whisper. They will fall through space in directions chosen by science and shaped by ambition. Travelers will look upon the swirling curves of space-time the way ancient sailors once studied the wind. And just as the wind once opened the world, the geometry of time and distance may open the stars. We are only at the first page of that story. But every precise calculation, every gravitational wave detection, every slingshot maneuver is a small footstep on the path that leads away from Earth and toward the wide unknown. Gravity reminds us that the universe is navigable. We only need to learn the deeper routes. To shape space-time, we must first understand that it is not a passive backdrop. It is active. It is responsive. It listens. Every star, every atom, even every photon tells space-time how to curve, and space-time in turn tells everything how to move. That conversation is constant. If we can learn to speak the same language, we can become participants instead of mere observers. We can bend the road instead of crawling along it. The idea of gravity as engineering may feel like magic, but we already use the earliest pieces of that magic. When scientists built the great detectors that observe gravitational waves, they did something astonishing. They measured the stretching and squeezing of space-time itself. A wave from two colliding black holes warped our planet by a tiny fraction of an atom. Our instruments felt that change. That is a beginning. It means gravity is not untouchable. With enough precision, we can detect and respond to curvature. To go further, we must learn to manipulate the quantum vacuum. Negative energy must be created in forms far more robust than a pair of metal plates pressed close together. Imagine machines that sculpt vacuum fields the way a potter shapes clay. Coils of light, perhaps laser grids, humming with silent power, holding regions of geometry in tension. These would not be engines in the traditional sense. They would be generators of curvature. Materials will matter as much as mathematics. The walls of a warp bubble or the throat of a wormhole will require matter that can survive both outward curves and time shifts. Our present materials are built to face ordinary forces. Steel and carbon composites would tear like paper under the strain of exotic geometry. We will need new phases of matter discovered under extreme pressure in the hearts of stars, or called into existence using quantum control. Matter that ignores the ordinary rule that gravity must always pull downward. Matter that joins the vacuum in defying expectations. Quantum computers may become the steering systems of the future, not because they compute faster, but because they can process information that interacts with spacetime at its smallest scales. The geometry of a warp field might require continuous adjustment far beyond the ability of classical machines. Quantum logic could whisper directly to the foam of reality, regulating fluctuations as they appear. Some researchers imagine gravitational manipulators that act like magnet coils around a superconducting ring. Instead of bending charged particles, they would bend spacetime. Superconductors already produce magnetic fields powerful enough to levitate heavy objects. Perhaps future experiments will reveal a connection between superconductivity and curvature. If a field can organize electrons into a unified wave, maybe a field can organize spacetime into a requested shape. All of this sounds distant, yet every great technology seems impossible until the first prototype appears. The challenge ahead requires merging general relativity with quantum field theory, something physicists are still struggling to do. Gravity belongs to the continuous fabric, while quantum mechanics belongs to the jittering dance of particles. To master exotic propulsion, we must bridge these worlds. We must understand how geometry behaves when energy is both wave and particle, and the vacuum is alive with possibility. There is also a practical concern. How does a civilization even begin to experiment with technologies that reshape spacetime? Safety must come first. A small miscalculation might create a bubble that expands uncontrollably, or a region where time slows unevenly, trapping the experimenters inside a moment that never ends. The earliest experiments will be tiny and cautious, gentle nudges rather than violent twists, a fraction of a grain of curvature instead of a plunge into the unknown. Machines that bend spacetime may never look like rockets or shuttles. They might resemble laboratories, rings of equipment surrounding an empty platform, a ship placed at the center where nothing appears to happen until the geometry responds. No sound, no flames, no movement. Only the silent flicker of a distant star suddenly growing closer. The shift from chemical thrust to geometric command is the difference between throwing a rock and shaping a river. It requires patience and precision instead of power. The engineers of tomorrow will need to be part mathematician and part artist, creating curvature fields that are as much sculpture as science. Some thinkers propose that the earliest warp technology might not move a ship at all, but rather enable communication. A tiny controlled fold in spacetime could shorten the path for a signal, allowing instantaneous conversation across light years. That would be a revolution on its own. Information would no longer crawl at the pace of photons. Knowledge would leap. Cooperation between distant worlds would become effortless. Such communication systems would demand less energy than full travel, making them the first stepping stone to the stars. Artificial gravity control could also change life on Earth. Imagine buildings protected from earthquakes by stabilizing the space-time beneath them. Imagine medical devices that relieve pressure on bones by gently adjusting the local curvature. Hospitals could create pockets where gravity is softened for healing, or strengthened to maintain bone health for those returning from long missions in space. Gravity would become a tool, like light or electricity, harnessed for human need. To manipulate gravity is to command the fundamental architecture of reality. The power is enormous, but so is the responsibility. We would need strict rules guided by wisdom, not ambition. The history of technology shows that capability always arrives before understanding. Fire came before firefighting. Engines came before traffic laws. The mastery of geometry would demand a cautious approach, unlike any we have taken before. Because when you work with space-time, the mistake is not a broken machine. The mistake is a broken path through the universe. Yet the reward inspires ambition. A future where distance and difficulty no longer imprison us on one fragile planet. A future where the solar system becomes our garden and the galaxy our playground. A future where gravity is not an obstacle, but an ally that we invite on every voyage. When engineers of the future stand before the first true curvature drive they will be taking, humanity's most significant leap, they will switch on a machine that asks the universe to open. And if the universe answers, then darkness between stars will lose its power over our curiosity forever. Chapter 7 closes with a simple truth. To travel the cosmos, we must learn to build with gravity. And once we do, the architecture of space-time will become the greatest invention of all. Every bold technology begins as a quiet measurement. Before steam engines, there were simple observations of boiling water lifting a lid. Before electric power, there were sparks dancing from amber rubbed with cloth. And before humanity reshaped space-time, there must be instruments capable of detecting its faintest whispers. We have entered that stage already. We have begun to hear the universe speak in the language of gravity. The turning point came when the Laser Interferometer Gravitational Wave Observatory heard the first gravitational wave. Two black holes collided in a distant corner of the cosmos. The energy released was so immense that space-time rippled outward in every direction. When those ripples reached Earth, they stretched and squeezed the planet by a fraction smaller than a proton. Yet our detectors noticed. We built machines sensitive enough to feel the heartbeat of merging black holes. For the first time, we listened directly to the geometry of the universe changing. That success opened a new chapter. If we can measure the motion of space-time, then one day we can guide it. These observatories are like primitive ears learning the grammar of curvature. Every new detection is a sentence from nature, teaching us how gravity carries energy and momentum. Meanwhile, a different type of instrument has grown in power. Atom interferometers allow us to track the positions of atoms with astonishing accuracy. When gravity changes slightly, those atoms fall or drift in measurable ways. Lakes of ultra-cold atoms trapped in magnetic bottles can reveal the geometry of space itself. These experiments are not yet warping reality, but they are mapping its texture with increasing detail. They are showing us how the smallest particles respond to the stretching of space-time. In laboratories, scientists have cooled atoms to near absolute 0 degrees Celsius, where their quantum behavior expands into visible waves. These waves can be split and reunited, creating patterns that shift if the atoms travel through regions with different gravitational potential. The experiment becomes a tiny voyage through geometry. If we learn to manipulate what those atoms experience, we take our first steps towards shaping space-time at will. We have also begun to explore the limits of the vacuum. Light bouncing between mirrors in quantum experiments alters the vacuum energy between them. That effect is faint but real. When we place two surfaces extremely close together, the vacuum pushes them inward slightly. This demonstrates that space itself contains a reservoir of energy that responds to boundary conditions. That discovery is not directly a warp bubble, but it is the same type of influence we must eventually amplify. Every measurement teaches us caution. Instabilities appear when negative energy becomes too deep or too unbalanced. Geometry snaps back to a normal shape quickly. The vacuum resists distortion the way skin resists stretching. This resistance is why space-time remains stable enough to support galaxies and life. But it also tells us the thresholds we must overcome to reshape distance. In some laboratories, scientists chase clues hidden in superconductors and electromagnetic fields. A strong ring of current might create more than a magnetic halo. It might nudge space-time itself. Results so far are inconclusive. Some claim tiny anomalies. Others detect nothing at all. What matters now is persistence. The first demonstration of curvature control will likely be a slight change in time flow or a microscopic contraction of distance. That moment will be quiet yet world-changing. The most exciting truth is that our tools are improving rapidly. Gravitational wave detectors will soon measure not only collisions of black holes, but also subtle waves from spinning neutron stars. Space-based detectors will listen to deeper frequencies that shake the very structure of galaxies. Precision timing of pulsars scattered across the sky may create the largest gravitational antenna ever imagined. The more we measure, the more we understand. The more we understand, the more we can attempt. There is another frontier waiting. Quantum gravity, the theory that unites the smooth curves of general relativity with the rattling energy of quantum mechanics. We do not yet possess that theory fully, but every new clue hints at how space-time may behave when bent into extreme configurations. When that theory is complete, gravity will no longer be mysterious, it will be programmable. Someday engineers might sit at consoles adjusting parameters that control geometry fields. They will run simulations that predict how a warp bubble will evolve moment by moment. They will design safety measures that prevent runaway distortions. They will turn gravity from a universal constant into a flexible tool. Our laboratories are not yet capable of such feats, but they are building the foundation. The precision we have achieved would be unimaginable to scientists only 100 years ago. A gravitational wave detection was once pure fantasy. Now we observe them regularly. A warp bubble is fantasy today, but tomorrow it becomes research, then theory, then testbed, then ship. If humanity continues to explore instead of shrink away from challenge, we will discover much more. We must keep building better detectors. We must keep questioning the vacuum. We must keep pushing the boundary where physics meets imagination. What begins as a ripple in a detector may end as a doorway to the stars. We have spent many chapters imagining how to reach distant worlds. Yet before we travel farther, we must pause and ask a deceptively simple question. What does faster than light truly mean? The speed of light is not just a number, it is a boundary between what can influence what. It is the fence that protects cause from effect. So when we talk about outrunning light, we must be careful. There is more than one kind of speed. The first is local speed. This is the speed measured by a traveler holding a stopwatch and a ruler. It is the speed you feel in your own ship. Special relativity says nothing with mass can exceed the speed of light by that measure. If you try to push harder, time itself slows within your frame, so the universe always sees you falling short. Light wins by definition. It is the standard against which all motion is judged. But there is also global speed. This is the change in separation between objects that do not share the same patch of space-time. Distant galaxies move away from us faster than light right now, because the space between us and them is stretching. They do not feel a wind. They are not fired from a cosmic cannon. The universe itself grows and carries them with it. No law is broken, because local physics remains peaceful and calm. The distance changes faster than light could cross, but nothing in that distance is racing a photon and winning. This difference creates confusion. A ship inside a warp bubble could remain still according to its crew, and yet arrive somewhere before any beam of light could have. Locally, nothing exceeds light's pace. Globally, the change in position is astonishing. We must learn to think in terms of geometry rather than motion. When space itself becomes the conveyor belt, the idea of speed becomes stretchy. There is another distinction: travel versus communication. Traveling faster than light may not violate causality if information cannot outrun light in a way that creates paradox. Imagine a warp bubble that jumps ahead of a photon but cannot send a message back into the bubble until ordinary light arrives later. You have moved swiftly, but you have not altered the order of cause and effect. You have not spoken into the past. The universe may allow such journeys even if it refuses any channel that sends a signal backward in time. To understand why the universe defends causality so fiercely, imagine a loop of information that goes wrong. Suppose a signal arrives before it was ever sent. Suppose instructions appear without origin causing themselves. Logic fails. Physics collapses into contradiction. The universe is allergic to such loops. Every successful theory of gravity and quantum mechanics preserves causality at its core. So any future travel technology must operate within that protection. We can bend space-time, but we cannot tangle time itself. Many misunderstand the phrase faster than light because they imagine a spaceship with thrusters glowing blue, blasting forward at impossible velocity. That image is wrong. Nothing real will ever streak through ordinary space faster than light. Instead, we must. Think of the light cone, the shape formed by every possible direction light can travel from a point. Staying inside that cone means respecting causality. Warp travel and wormholes find new geometry where the arrival point lies inside a new cone, even though it once lay outside the old one. The structure of possibility itself shifts. The rules widen, but never break. Even today, our technology plays with the edges of these distinctions. In satellite systems, time passes slightly differently because gravity is weaker in orbit. Without correcting that difference, communication would become inaccurate. Pilots of deep space missions account for how space-time curves around planets. Every time we use these tools, we remind ourselves that distance and duration are not fixed. They are negotiable. We learn slowly how nature allows shortcuts. Information transfer is the strictest test. If a person or machine travels via a wormhole and sends back knowledge before it was learned, nature may intervene. Some theories predict surges of energy that would seal the wormhole shut. Others suggest that probability itself rearranges to prevent contradictions. These protections may close the path of time travel while leaving spatial travel intact. The most likely future is one where ships cross light years quickly, but messages remain bound to causality. We arrive early, but cannot report success until later. A strange balance, but a safe one. Ask a physicist whether faster than light travel is allowed, and many will say no. But ask whether space-time can shorten a path so the trip takes less time than light would normally need, and the answer becomes maybe. Ask whether expansion can make two galaxies separate faster than light, and the answer becomes yes. Ask whether geometry can bend to create a tunnel that drops a traveler into a distant star system, and the answer becomes, it depends on negative energy. The deeper we look, the more the boundary blurs. Perhaps the real truth is this: faster than light travel is not really about speed at all. It is about access. It is about reducing separation to the point where the light limit feels irrelevant. If your journey takes days while light would take decades, you experience a new ease of motion, even though every local rule remains unchanged. You navigate space-time as it shapes itself. There is beauty in that realization. Light remains the messenger that never fails. It remains the guidepost for causality. Yet imagination no longer bows to its speed. We are not chasing photons. We are rewriting the map they follow. Someday, children may learn that the speed of light is the fastest anything can travel through space. And in the same lesson, they may learn that the smartest way to explore is to avoid traveling through space at all. Travel becomes transformation. Motion becomes geometry. Faster than light then becomes a phrase like flying. Once flying seemed impossible because humans are heavy and air is thin. Then we learned that motion can be generated through lift, not muscle. The laws of physics did not change. Our approach did. The same shift awaits us in the stars. Light will keep its crown as the ultimate runner. We will simply choose different races, different game boards, different definitions for what it means to arrive. The universe does not forbid reaching distant worlds quickly. It only insists that we do so with respect for the order of events. As long as cause remains the parent of effect, the cosmos keeps its dignity. Within that dignity lies enormous freedom, and that freedom sings to our curiosity. For most of human history, the night sky has felt like a wall, a glittering boundary reminding us how small we are and how far away everything else remains. The stars shine with ancient light, telling stories from across the abyss. We have always imagined reaching them, but imagination often bowed to fear. Fear that distance is destiny. Fear that physics has locked us on a single world forever. Yet the deeper we have explored the rules of nature, the more those fears dissolve. The universe does not punish ambition. It challenges it. The speed of light once looked like a barrier carved into the heart of reality. Now it reveals itself as a signpost pointing toward new methods of travel. The cosmos does not forbid journeys among the stars. It simply insists that we stop thinking like creatures bound to rockets and engines. It asks us to think like space-time itself. Gravity stretches, geometry folds, time bends. These are not poetic metaphors. They are facts. They are tools. They are invitations. We know that no ship can outrun light while remaining inside the structure of ordinary space. Local motion is held in check to preserve cause and effect. But we have discovered that space itself can move without resistance. The universe showed us this truth in the first instant, after the Big Beginning, when inflation pulled everything apart faster than light could chase. It shows us again at the edges of the observable cosmos, where galaxies recede beyond contact. Gravity wrote faster than light behavior into the story from the opening chapter. Wormholes remind us that distance can collapse. Warp bubbles remind us that space can flow. Gravitational slingshots remind us that cleverness can replace force. Time dilation near massive objects reminds us that a short personal journey may still leap across epochs. The tools are scattered everywhere in nature like hints left by a generous teacher. Each clue says the same thing. You are not trapped, you are invited. The deepest secret is that space-time is flexible. It can be curved by mass. It can be nudged by energy. It can be guided by information. Someday it may be shaped by technology. What looks like impossible travel from one perspective becomes a natural slide from another. Instead of speeding up, we shorten the road. Instead of breaking rules, we learn how the rules bend. Negative energy remains the most difficult ingredient. It asks us to draw power not from fuel, but from the restless potential of the vacuum. That challenge is enormous. The cosmos protects such forces with strict accounting. But history teaches that every mystery eventually yields to understanding. We once believed that flying was a violation of nature. We once believed that splitting the atom was unthinkable. We once believed that sending signals across the globe instantly was fantasy. Now those impossibilities are forgotten conveniences. When humanity learns to manipulate curvature, we will leave behind the era of rockets and sails. Ships will glide in silent calm through stars that shift outside the windows. There will be no flames, no shaking, no struggle, just geometry flowing like water. A journey will feel like a moment of rest while the cosmos itself moves. Destinations will approach, not because we rush, but because distance relaxes its grip. The implications for life and culture will be profound. Earth will become a birthplace rather than a boundary. The solar system will become a neighborhood. The galaxy will become home. Isolation will end. Curiosity will thrive. Civilizations could meet long before their light ever reached each other. Knowledge will travel faster than ignorance. Cooperation will replace solitude. Our species will grow into its potential, not as guardians of one small world, but as participants in a vast community that spans the stars. We must also imagine responsibility. Controlling space-time is the greatest power any civilization could wield. It demands wisdom that grows alongside capability. We must build not only machines but principles. We must ensure that exploration respects the structure of time and the health of worlds. The technology that frees us from distance must also protect the continuity of reality. Gravity bends willingly when asked politely. It crashes down when forced. Understanding must come before ambition, but ambition must never fade. The final truth is both humbling and empowering. Light remains the fastest traveler through normal space. That will never change. But travel does not have to mean moving through normal space. It can mean changing what normal means. The boundary drawn by light is not a cage, it is a step. Once we learn to step sideways into geometry itself, the speed of light becomes a reference rather than a limit. The universe set the rules. The universe also provided the loopholes, and those loopholes shine like stars, waiting for the first human vessel to arrive. As we stand now at the very beginning of this new era, we face one simple question. Do we accept distance as final, or do we treat distance as a problem asking for a clever answer? Everything we have discovered suggests the answer is within reach. The universe allows creativity. It rewards curiosity. It opens doors to those who learn how to see them. Look up at the night sky. Every point of light is a promise. Every distant world is a future. The stars are patient. They wait. They have always been waiting. And when the first ship bends space-time and appears at a new sun with a quiet ripple in the dark, the universe will simply smile, for it knew all along that we would arrive.